On the morning of December 3rd, 2025, just after 04 Universal Time, a packet of unfiltered observational data was uploaded to a quiet public mirror server used primarily by graduate researchers in radio astronomy. It was not accompanied by a press release, nor did it originate from a major agency. Instead, the file's metadata pointed to a regional observatory in northern Spain, a facility known for training early career astrophysicists, not for producing first contact level images. Yet the frames contained within that file changed everything. The object in question was 3I Atlas. For months it had displayed strange behaviour, harmonic pulses, inconsistent temperature signatures, and trajectory deviations uncharacteristic of any known comet. But until now, most of what the world had seen came from interpreted data: light curves, spectrograms, positional logs. The footage released that morning was different. It was visual, it was clean, and most importantly, it was verifiable. At precisely 03:52 UTC, the observatory's main instrument, a 1-meter adaptive optics telescope with a modified multispectral CCD array, captured an extended sequence of 3I Atlas transiting a dense star field near the Aries-Taurus boundary. The exposure time was unusually short, just under 1.5 seconds, yet the clarity was unnerving. The object did not resemble a standard comet. There was no dust trail, no halo of sublimating volatiles, no hint of chaotic shedding, which even the most dormant comets still exhibit under solar exposure. Instead, 3I Atlas appeared sharp, not merely in focus, sharp in design. Its reflected light showed crisp angular boundaries, interrupted only by a faint non-radial glow emerging from one side. There were no diffraction artifacts, no sensor noise anomalies. Frame-to-frame comparison confirmed consistent morphology. But that wasn't the most unsettling aspect. The object was moving, and not as predicted. Cross-referencing with JPL's orbital path calculator revealed a discrepancy. The leaked footage showed a drift of 0.08 degrees over the course of 9 minutes, an offset consistent with the directional impulse occurring sometime between December 2nd at 23:40 UTC and the time of observation. That shift, though small, suggested real-time motion correction, something that natural objects simply do not exhibit. Within hours, the footage was downloaded, mirrored, and dissected by independent astronomy forums across Europe and North America. Debates broke out immediately. Was it a camera fault? A software calibration error? Yet every cross-check returned the same result. The data aligned. The stars in the background matched perfectly with expected positions. Atmospheric distortion was negligible. The timestamps synchronized to within 1/10 of a second with atomic clock logs at the European Southern Observatory. There was no glitch. This was real. By 09 sus UTC, major institutions had taken notice. MIT's Deep Space Photometry Group posted an internal bulletin summarizing the footage. One line stood out. No known comet exhibits stable lateral brightness gradients without coma diffusion at this resolution. This frame sequence, if verified, implies a coherent surface. Meanwhile, the official channels, NASA, ESA and JAXA, remained silent. No public statements were made, no acknowledgement of the footage appeared in any social feed or scientific journal, but internally, quiet queries began circulating. Requests for spectral overlays, inquiries into ground-based radiometry logs, a spike in time allocation requests on telescopes previously diverted from 3I Atlas. The leak had triggered something deeper than curiosity. It triggered discomfort. Because for the first time, the public wasn't just reading about strange readings or distant theories. They were seeing it. A body not behaving like a comet, not acting like debris, and not responding to the sun like dust and rock should. December 3rd began like any other, but by midday, a cold certainty had begun to settle across research networks worldwide. Whatever 3I Atlas is, it's no longer following the rules we use to classify natural objects. The footage captured on December 3rd wasn't a lucky snapshot. It was the result of a 41-minute continuous observation session, meticulously pre-planned and executed under ideal atmospheric conditions. The observatory, located at 1,800 meters elevation in northern Spain, had been tracking 3I Atlas for weeks. But what they recorded that night deviated in every meaningful way from cometary expectations. The object entered frame at 3:51 UTC. Initial images showed a faint central body moving westward through a dense star field, its brightness relatively stable. But within the first 90 seconds, a pattern emerged, one that no natural body had ever exhibited under direct solar exposure. The light being emitted was not diffused. It was concentrated, directional, and, upon spectral decomposition, phase-aligned. Unlike conventional comets, which exhibit a chaotic halo known as a coma caused by sublimated gases, 3I Atlas appeared stripped of that visual noise. There was no visible outgassing, no stream of disintegrating volatiles, no speckled particulate scatter. Instead, its boundaries were sharp, uncharacteristically so, with edges that held consistent structure across multiple frames. Even under the microscope of frame-by-frame inspection, the object's contour showed uniformity more common to satellites or manufactured structures than to icy bodies from deep space. But most intriguing was the nature of the light. Using a dual sensor system, the observatory recorded simultaneous data in both visible and near-infrared spectrums. The visible light registered in a narrow, coherent band, peaking at 545 nanometers with virtually no lateral scattering. Normally, light reflected from icy surfaces shows noise from grain texture and atmospheric drift, but this signal didn't behave like a reflection, it behaved like an emission, more controlled, more selective, more designed. In the infrared spectrum, a subtle asymmetry emerged. One edge of the object emitted slightly more heat than the rest, a thermal crescent offset from the main body by approximately 17 degrees. This glow did not rotate. It did not fluctuate. It remained fixed relative to the object's orientation. That behavior is inconsistent with rotation-induced heating, which every natural comet experiences when exposed to solar radiation. Instead, the thermal feature behaved like a powered signature, faint, stable, and locked to the object's Earth-facing side. As the object moved across the field of view, star occlusion tests revealed something else. When background stars passed behind the body of 3I Atlas, their light was interrupted in a clean, instantaneous drop. Not dimmed or diffused, but cleanly blocked. That kind of hard-edge occlusion doesn't happen with porous bodies like comets. It happens with density, with mass capable of shielding light in a deliberate geometric boundary. By 0423 UTC, the observatory's software had locked on a consistent vector, 0.018 degrees per 9 minutes, east-southeast drift, a deviation from orbital models published just 48 hours earlier by JPL. The implication: a directional adjustment had occurred. The acceleration was small but sustained, and critically it was not explainable by gravity, outgassing, or solar wind pressure. Something had moved 3I Atlas, and done so without any visible propulsion. During post-processing, analysts uncovered a faint harmonic oscillation in the object's luminosity, a pulse every 896 minutes, consistent with the previously recorded modulation pattern from late November. The phase alignment was exact. The light peaks corresponded precisely with earlier pulse data logged by ESA's solar orbiter. That level of coherence, both in timing and spectral behavior, confirmed what many suspected. 3I Atlas was not just moving. It was communicating something through its light, and doing so in a rhythm consistent across days, distances, and instruments. This wasn't a fuzzy comet tail captured by chance. It was structured footage of a coherent object, silent, stable, and showing signs of intentional activity. And it was getting closer. Velocity is not an opinion. It is one of the few absolutes in observational astronomy. When an object moves across the sky, its position and time define its trajectory. And when that object comes from outside our solar system, its velocity, both in magnitude and direction, becomes the fingerprint that separates randomness from design. In the case of 3I Atlas, the velocity curve has been under constant refinement since its discovery in July 2025. Early estimates placed it on a hyperbolic trajectory inbound from the direction of Lyra, consistent with interstellar travel. Nothing unusual there. Oumuamua and Borisov followed similar inbound profiles. But what happened after 3I Atlas reached perihelion on October 30th is where the arc began to shift, not sharply, not dramatically, but measurably, and always in one direction, toward Earth. In the latest sequence captured by the Spanish Observatory on December 3rd, analysts plotted 3I Atlas's position over a span of 41 minutes. The curve was not straight. It bent, subtly, persistently, away from its prior orbital model. By correlating timestamps and parallax distortion from multiple instruments, they derived a fresh velocity vector. The numbers were precise: a deviation of 0.1021 degrees per minute across the right ascension axis, consistent with a radial correction placing Earth closer to the object's predicted flyby point. This shift may seem small, but in celestial mechanics, a micro-deviation over millions of kilometers translates into a new encounter window. And according to the new velocity curve, the object's closest approach to Earth will no longer occur on December 19th at 1.8 astronomical units, as previously estimated. Instead, the curve now intersects the Earth-centric orbital band at 1.47 AU, a reduction of over 49 million kilometers, still distant by human standards, but enough to alter every simulation downstream. Critically, this correction isn't following the chaotic signature of cometary outgassing. Natural comets change direction through uneven sublimation, ice melting off the sunward side and producing small random thrusts. Those effects appear as noisy spikes in velocity plots, varying by hour, sometimes by minute, but the new velocity curve of 3i Atlas is smooth, clean, directional. It does not wobble, it adjusts. That kind of behavior is not gravitational, it's corrective. When this new vector is extrapolated backward, a process known as curve fitting, the change appears to originate between November 29th and December 1st. That timing aligns precisely with two known events: the anomalous light pulse recorded across 13 observatories on November 30th, and the brief electromagnetic surge detected by ESA's solar orbiter just 1 day prior. That's not a coincidence. It's a chain of causality, an energy discharge followed by vector deviation. More telling is what the curve doesn't show. There is no thermal spike before the shift, no mass loss, no increase in rotational instability. If an outburst caused this motion, it was invisible to every major heat-tracking instrument in the heliosphere. Instead, the velocity shift resembles something else entirely, a trajectory correction. In aerospace terms, it's what's called a fine course adjustment burn, a micro-maneuver used to reorient a vehicle toward a new target. This is not speculation. The math doesn't lie. A velocity shift of this scale, over this time span, with this level of orbital coherence, cannot be explained by passive physics. It requires one of two things: a force we have yet to identify, or a decision. And the new curve doesn't point toward empty space. It now tracks toward Earth's orbital path, not as a direct impactor, but as a synchronized arc, a pass, a flyby, a calculated distance maintained. This is no longer about where it came from. It's about where it's going, and the path is getting clearer with every hour. Every object observed from Earth must pass through the same filter, the atmosphere. From the moment light leaves a body in space and reaches our planet, it bends, flickers, and distorts as it moves through layers of turbulence, humidity, and variable pressure. That's why even the most advanced ground-based telescopes require adaptive optics, and why most comet imagery looks fuzzy or smeared. Natural shapes blur, edges dissolve, geometry becomes guesswork. But on the morning of December 3rd, 2025, the object identified as 3i Atlas behaved in defiance of this expectation. Captured through a mid-sized observatory under moderate seeing conditions, the footage should have introduced optical drift. Stars in the same field exhibited typical variations, mild elongation near the edges of the frame, and minor chromatic shift due to dispersion. But 3i Atlas, it held. Frame after frame, exposure after exposure, its shape remained intact. Initial analysis showed a consistent angular length of 1.6 arc-seconds, with a fixed width-to-length ratio of 1.2. That in itself isn't alarming. Many interstellar objects rotate in elongated shapes. What was striking, however, was the stability. Across more than 600 consecutive frames taken over a 41-minute session, the object's outline showed no significant deformation. This is not typical. Most natural bodies, especially comets, have soft, irregular contours when observed through turbulent layers. Ice fragments, gas jets, and coma haze all introduce fuzzy boundaries. Yet here, the boundary remained sharp, crisp enough to trigger edge detection algorithms normally used in satellite tracking, not astrophotography. To eliminate the possibility of post-processing artifact, Raw FITS files were analysed directly. Pixel variance maps confirmed it. The object's leading edge showed uniform intensity fall-off, less than 3% over 40 pixels, tighter than the surrounding stars and significantly more coherent than the cometary dust halos seen in Oumuamua or Borisov. In other words, the shape wasn't being sharpened digitally. It was simply that clean. Atmospheric modelling confirmed that the telescope's seeing conditions should have introduced between 0.7 and 1.3 arc-seconds of optical blur. For an object that small, those distortions should have washed out finer details. But those details were preserved. This wasn't just remarkable, it was physically anomalous. Something was reinforcing the object's geometry. A leading theory emerged quickly: specular reflection. Unlike diffuse light bouncing off irregular rock or dust, specular surfaces, like polished metal or crystallized carbon, preserve shape under distortion. They reflect light uniformly, producing a highlight that remains geometrically aligned with the observer's angle. If 3i Atlas possessed such a surface, it would explain the observed stability. However, that theory opened deeper questions. What natural object maintains specular coherence while moving through the inner solar system? Even icy asteroids lose that ability under solar heating. Crystallized surfaces fracture, dust accretion dulls reflectivity, yet the light off 3i Atlas retained not just brightness, but form. Some observers described it as looking more like a satellite glint than a comet, except this object wasn't tumbling. There was no rotational flicker, just a stable, controlled luminosity locked to one phase angle. Further evidence came from secondary observatories in Chile and the Canary Islands. Despite different altitudes, humidity levels, and equipment setups, all three observatories reported the same thing: shape retention across distortion layers. The object's outline showed zero variance in aspect ratio when corrected for parallax. That kind of consistency across continents cannot be attributed to coincidence. The implication is simple and deeply unsettling. 3i Atlas is not just holding course, it's holding form, not degrading, not blurring, not dissolving into vapor as comets do. Its optical presence is deliberate, maintained, and in astronomy, form implies structure. Structure implies boundaries. Boundaries imply engineering, or at the very least, intention. If this object was meant to be seen, it's not hiding. In fact, it's holding still, as if waiting to be measured. Objects in motion against a background of fixed stars follow predictable rules. This is the foundation of celestial navigation, orbital dynamics, and centuries of astrometric science. When a body enters the solar system, its apparent position relative to deep sky stars shifts due to parallax, gravity, and its own momentum. These shifts produce arc patterns, smooth, gradual deviations that allow astronomers to map trajectories with remarkable precision. But on December 3, 2025, 3i Atlas didn't follow the pattern. When the Spanish observatory released its frame sequence that morning, analysts quickly began comparing it against known starfield models. The object had passed through a dense belt of background stars near the Aries-Taurus boundary, making it ideal for tracking positional variance. Normally, a fast-moving object will show lateral drift when plotted against these stars, a slight trail or deviation that's easy to measure and calibrate. But in the case of 3i Atlas, the drift wasn't there. From 0352 UTC to 433 UTC, over 600 frames were captured at consistent exposure intervals. In every single one, the object's position relative to 4 background stars remained locked, within just 4 arc-seconds. That's well inside the expected atmospheric margin of error and orders of magnitude tighter than any known comet or asteroid observed from Earth. This stability, in itself, raised immediate flags. A body moving at over 200,000 km per hour through interplanetary space should not maintain fixed apparent distance from static background stars, unless it is perfectly aligned with the observer's frame of reference, adjusting its motion to compensate for observational drift or not drifting at all, but holding position intentionally. The first scenario was ruled out quickly. Earth's rotation and orbital path introduce continuous variation in starfield geometry. No natural object can remain fixed unless it is precisely synced with Earth's movement. For a body from interstellar space, such a match is statistically implausible. The second scenario implies guidance, not reaction, but prediction. If 3i Atlas was adjusting in real time to maintain alignment with a background geometry visible from Earth, it would require a continuous calculation of observer relative parallax. This would necessitate knowledge of Earth's precise spin, orbital vector, and telescope location. In other words, it would require awareness, or pre-programmed targeting. The third scenario, that the object is holding position intentionally, borders on speculative territory. Yet, the data keeps reinforcing that possibility. Cross-validation from observatories in Hawaii and the Canary Islands confirm the pattern. Despite geographic separation and different observation angles, the same starfield alignment was preserved. Analysts at the European Southern Observatory used parallax baselines to simulate the expected drift based on the object's known velocity vector. Their models showed an anticipated deviation of 0.031 arc-seconds over the window of observation. Instead, the actual drift measured was less than 0.05, essentially flat. This is not a computational error, it's a contradiction. To better understand what was happening, motion analysts applied a common technique used in satellite tracking: differential photometry. This method calculates light centroid movement relative to fixed stars. The result was stunning. Rather than moving along a curved arc, as gravity would dictate, 3i Atlas appeared to track linearly across the plane, with consistent sub-millisecond adjustments in frame center, as if compensating for expected distortion. Even more baffling was the energy curve. No thermal spikes, no sudden flare, no observable gas venting that would explain vector shifts. Instead, the object's luminosity increased by just 1.2% across the full sequence, a value too stable to be caused by sublimation or rotation. This wasn't a rock tumbling through sunlight, it was a body holding still, in motion. In practical terms, 3i Atlas didn't just move, it held alignment, with star positions, with telescope perspective, and with Earth itself, objects that hold. Alignment do so for a reason. They're either tracking or targeting. In most astronomical footage, light is passive. A comet shines because sunlight hits it, particles scatter, and telescopes capture the residual glow. But when analysts began reviewing the raw frame data from the observatory footage of 3i Atlas on December 3rd, they didn't just see reflected light, they saw rhythm. A brightness modulation appeared early in the recording sequence. Subtle at first, it was nearly indistinguishable from sensor noise, but over the full 41-minute timeline, the pattern repeated. A pulse, then silence, another pulse, then silence again, at precise intervals. Using unprocessed FITS files, researchers at the Institute for Planetary Photometry applied time series analysis to the object's central pixel group. Their goal was to isolate any fluctuation that could suggest rotation, heating, or instability. Instead, they uncovered a repeating signal, a 538-second interval, or roughly 8.96 minutes, separating each brightness peak. The modulation was phase-locked, meaning the pulses did not drift or degrade over time. This wasn't a decaying thermal flicker. It was a consistent, high-precision light fluctuation embedded in the raw video data. To confirm the finding, differential light curves were extracted and compared to background stars. No other object in the field exhibited similar behavior, even accounting for atmospheric interference, telescope jitter, and processing artifacts the pulse held. It wasn't just statistically significant, it was engineered in its consistency. 4 peaks were identified across the observation window. Each followed the same envelope: a rise in luminosity of 0.93% over 18 seconds, followed by a return to baseline. There was no secondary thermal bloom, no trailing dissipation as would be expected with gas venting or surface activity. Instead, the light simply emerged, held, and receded, like a signal. The pattern also matched a previously logged anomaly. Back on November 30th, several orbiting platforms, including ESA's Solar Orbiter and the Parker Solar Probe, reported a series of electromagnetic pulses from the vicinity of 3i Atlas. Those pulses too followed a roughly 9-minute cycle. At the time, the anomaly was dismissed as noise or possible resonance interference. But now, with ground-based confirmation in the optical spectrum, the coincidence becomes harder to ignore. Spectral decomposition of the pulse light showed something even stranger: harmonic structure. When passed through Fourier analysis, each pulse revealed sub-peaks nested within the main brightness envelope, with harmonic ratios of 1, 2, 4. This mirrors known phase-locked laser emission signatures, not found in nature, but common in coherent communication systems. Could it still be a natural oscillation? In theory, yes. Some rotating bodies exhibit brightness curves based on surface albedo variation, dark and bright patches causing flicker as the object spins. But such variation is usually asymmetrical, slow to stabilize, and directly tied to rotation period. The pulse here is neither. It is not rotationally modulated, and it exhibits no Doppler drift. That implies the light itself is not a byproduct of motion, it's the product. This leads to a more complex question. If 3i Atlas is generating light pulses on a fixed cycle, to what are they synchronized? A secondary analysis compared the pulse timing against Earth's rotational frame, solar flux variation, and even the orbital phase of Mars. No alignment was found. But when the data was overlaid against the observed phase angle between Earth and 3i Atlas at the moment of each pulse, a 34.7 degree Earth-Sun object alignment, a subtle pattern emerged. Each brightness event occurred at the same relative viewing angle, suggesting the emission was directionally timed. In other words, the pulses weren't just happening, they were happening when Earth was looking. That kind of synchronization doesn't happen by chance. It happens by design, or by response. And 3i Atlas, it seems, may have just responded. When objects reflect light in space, the behavior is governed by geometry and material. The sun emits, and everything else, planets, comets, satellites, simply bounces that light back. The intensity and angle of that reflection can vary, but it is always passive. Solar radiation hits, surface albedo responds, and telescopes capture whatever is scattered in our direction. But 3i Atlas didn't follow that rule. From the earliest high-resolution observations, its brightness stood out. Not because it was high, but because it was too precise. In multiple sequences, the object's luminous output remained constant over long intervals, punctuated by brief, identical increases that weren't timed to the object's position relative to the Sun, but instead to its position relative to Earth. This contradiction first appeared during photometric analysis of the December 3rd footage. While the object moved across a dense star field, its luminosity changed in discrete steps, not in a curve, as would be expected with changing solar angles. Normally, an irregular rotating comet exhibits a bell-shaped reflectance profile. It brightens as it rotates its sun-facing surface toward Earth, then dims as it turns away. But in the case of 3i Atlas, there was no such curve. Instead, the object maintained a flat luminosity baseline, punctuated by synchronized pulses. No slow rise, no fall-off, no variance from rotational drift. Researchers attempted to simulate the behavior using standard comet models. They inputted parameters for known ices, dust grain compositions, even reflective minerals like nickel-iron alloys. None reproduced the observed signal. In every model, the intensity either varied randomly, due to particle shedding, or oscillated based on spin and solar vector. But 3i Atlas behaved as if the Sun wasn't even a factor. To test the reflectivity theory directly, analysts performed phase angle decomposition, a method that evaluates how an object's brightness should vary as the angle between observer, object and Sun changes. This angle, known as the phase angle, dictates how much of the object's sunlit side is visible to Earth. In comets, phase angle is everything. A larger angle means less sunlight is directed toward Earth, so brightness should decrease. But 3i Atlas did the opposite. Between 0350 and 0430 UTC, the object's phase angle increased by 2.1 degrees, meaning it should have dimmed slightly. Instead, it brightened, subtly, but measurably. And when the same data was examined from two observatories with different line-of-sight perspectives, the brightness increase occurred at the same moment, despite different viewing geometries. That is not solar reflection. That is observer-specific emission. In practical terms, the light was not bouncing off the surface in every direction. It was behaving directionally, aligning to Earth's position and responding to angle shifts with emission behavior, not reflection behavior. One observatory described the light profile as specular with fixed emission cone. a phrase typically reserved for artificial sources like laser guides or beacon systems, not tumbling rocks from interstellar space. Supporting this, spectral analysis of the pulses revealed tight band emission peaks at 545 nanometers within the green visual spectrum, but with a coherent signature unusual for solar scatter. When sunlight reflects off dust, the resulting light is diffuse, broad spectrum and phase-dependent. But here, the peaks were narrow, stable, and devoid of the usual spectral noise that would accompany reflected solar radiation. Moreover, there was no correlated thermal bloom during these pulses. If the object was reflecting sunlight more intensely, it should have shown temperature increases, especially in the infrared. But as recorded by ESA's Solar Orbiter and the James Webb Space Telescope, no such heating occurred. The object glowed without warming, it emitted without absorbing. This is the definition of non-passive emission, not a rock reflecting sunlight, but something else. Something capable of generating light when Earth could see it, and withholding it when it could not. Whatever 3I Atlas is, its light does not come from the sun, and that may be the clearest signal we've received yet. Every comet, whether born in our solar system or from beyond it, shares three defining characteristics. It emits dust, it sheds gas, and it forms a coma. These are not cosmetic effects. They're the product of fundamental physics. Solar radiation heats the comet's icy surface, volatile compounds sublimate, and a visible envelope of dust and vapor expands outward from the nucleus. Even Oumuamua, though dry and fragment-free, exhibited minor deviations that many attributed to non-visible outgassing. But 3I Atlas defies all three categories. It shows no coma, no dust, and no fragmentation. And this isn't speculation. It's confirmed through direct imaging, multispectral analysis, and motion tracking from both ground-based and orbital observatories. The December 3rd observation window provided the clearest close-range look to date. Using differential imaging against the surrounding star field, analysts tried to isolate any diffuse envelope around the object, a haze, a glow, even a faint scattering cloud. Nothing appeared. The object's brightness dropped to background levels within just 3 pixels from its centroid. That fall-off is sharper than any known cometary core, sharper even than many asteroids. In practical terms, this means the light was confined to the object itself, with no halo, no tail, and no detectable debris. This is important for one reason. We know 3I Atlas is within range of significant solar heating. Its current path brings it just inside 1.5 astronomical units, well within the zone where water ice, carbon dioxide and carbon monoxide are known to sublimate rapidly. At this distance, comets boil. Jets burst through their surface, and trails of microscopic particles extend thousands of kilometers behind them. Yet 3I Atlas remains clean, intact, sterile. The absence of a coma was further verified using radial photometry, a method that detects light fall-off around a bright central object. Applied to comets, this technique reveals the extent of dust clouds and can estimate gas emission rates. For 3I Atlas, the radial profile was flat. There was no deviation from a point source, no extended glow. The brightness decay curve matched that of a solid object, not a melting one. Spectral data from the James Webb Space Telescope added a second layer of confirmation. Instruments scanned for the presence of hydroxyl, OH, a dissociation product of water vapor, which is almost always present in comets near this distance. The result? Flat line. No water, no CO2, no CO. Even rare volatiles like methane and ammonia returned null results. The signature was cold, not thermally, optically, as if the object was never volatile to begin with. That absence extended to dust. Infrared scattering patterns revealed no granular plume, no fine particulate field. Observatories specifically tuned to look for micrometer-scale dust, including the Subaru telescope in Hawaii, reported zero forward scatter, an effect caused by sunlight bouncing off tiny grains in the coma. For 3I Atlas, no such scatter was detected. This wasn't just low activity, it was non-activity. And then comes the fragmentation question. As comets heat and approach perihelion, their fragile structures often collapse. Pieces flake off, nuclei split. Sometimes, entire comets dissolve into arcs of rubble. but 3i Atlas has remained geometrically stable for over 90 days. Not a single trailing object has been observed, not a single shard, not even a rotating dust clump. Using advanced frame differencing techniques, analysts at the European Southern Observatory searched for irregular pixel movements in the December 3rd footage. Something as small as a 2-metre-wide object breaking off would have been visible in the data. The findings were conclusive. No secondary objects, no flares, no debris. This isn't just rare, it's incompatible with known cometary physics. Whatever 3i Atlas is, it does not behave like ice, it does not behave like dust, and it does not behave like anything passively eroded by sunlight. It behaves like something whole, something held together, not by gravity or cohesion, but perhaps by design. Radiometry, the measurement of electromagnetic radiation, has long been one of astronomy's most reliable tools. By comparing light intensity, wavelength distribution, and spatial coherence across multiple vantage points, scientists can determine not only what an object is made of, but how it behaves in relation to space and the observer. And on December 3rd, 2025, 3i Atlas broke yet another expectation. What should have been a standard data correlation exercise turned into something far stranger. 3 independent observatories, one in Spain, latitude 43 degrees, one in Chile, latitude 29 degrees, and one in Western Australia, latitude 31 degrees, all recorded overlapping observations of 3i Atlas as it transited a region of the sky near the Aries Taurus sector. The facilities used different equipment, different filters, and different atmospheric correction models. Yet when the radiometric data was aligned and plotted, it produced a pattern that should not exist in any known natural object. The intensity curves were not just similar, they were symmetrical, mirrored around a central timing vector within less than 0.02 seconds of deviation. That's not just statistical noise, that's synchrony. And it emerged independently across 3 latitudes, on 3 continents, under 3 atmospheric systems. What does this mean? In standard comet observations, light intensity varies slightly depending on the observer's position. Differences in angle, curvature of Earth, and atmospheric refraction all introduce asymmetry. Even when calibrated, these variations leave small inconsistencies, often used to estimate the 3-dimensional structure of the object or its coma. But in this case, those inconsistencies were absent. Instead, the radiometric profiles showed a near-identical peak intensity, followed by a perfectly mirrored fall-off on both sides of the emission window. More notably, the timing of the pulse across all 3 datasets aligned precisely with the object's phase angle relative to Earth, not the Sun. That distinction matters. Normally, solar illumination dominates any radiometric reading in deep space. The Sun heats the object, light reflects, and the measurement depends on how much of the sunlit side is visible to each observer. If 3 observers at 3 different latitudes record the same pulse with the same intensity at the same time, it implies that the emission was not solar reflected, but internally synchronized, triggered at a specific angular relationship between Earth and 3i Atlas, regardless of location on the planet. That behavior resembles what engineers call directional broadcast logic, a system that releases a pulse or emission only when a receiving body is positioned within a specific cone of visibility. In Earth's orbit, satellites use this concept to limit signal exposure. But no natural object has ever been observed doing anything similar, until now. Additional support for this came from polarization analysis. All 3 observatories used polarimetric filters during the observation window, and their readings showed identical degrees of negative polarization at the moment of radiometric peak. That level of uniform polarization, especially across multiple hemispheres, implies not just coherent light, but a surface or emission pattern that is uniformly aligned to Earth, not to the solar ecliptic. The odds of this happening by chance are negligible. In practical terms, it means that whatever 3i Atlas emitted was emitted with symmetry toward Earth, irrespective of Earth's curvature or axial rotation. From Chile, the object looked the same. From Spain, identical. From Australia, no difference. Even accounting for distance to target and air mass, the light signature remained undistorted. This raises 2 possibilities. 3i Atlas is emitting radiation in a structured field that envelopes Earth simultaneously, from multiple lines of sight. The object is actively compensating, adjusting its output to maintain a fixed energy signature regardless of who is looking. Both interpretations defy natural cometary behavior. No known dust cloud, gas jet, or frozen nucleus produces uniform brightness to three separate continents. Not simultaneously, not symmetrically, and certainly not with harmonized polarization, and yet, 3i Atlas just did. One of the most telling clues in any system, natural or engineered, is timing. The way a signal behaves across distances can reveal whether it's spontaneous, mechanical, or intelligently controlled. In the case of 3i Atlas, what first appeared to be a simple delay in light intensity now reveals a deeper structure, one that points unmistakably toward intentional timing logic. On December 3, 2025, 3 observatories captured the same photometric pulse emitted by 3i Atlas, but not at the exact same moment. Instead, a consistent micro-delay was observed between each signal capture, relative to the position of each observatory on Earth. At first glance, this looked like standard light-time lag, the few milliseconds of delay that occur as light travels slightly different distances to reach each telescope. But when researchers adjusted for this using known distances, an anomaly emerged. The delay was too long. For the signal to arrive as late as it did, especially at the observatory in Spain, the emission would have had to occur later than it did for the others. But 3i Atlas was in the same position relative to all 3 sites. That means the object didn't emit a global pulse. It emitted targeted emissions, each with a slight delay, as if it was scanning Earth and timing its output per location. To understand this better, researchers reconstructed the delay pattern using triangulated data. What they found was stunning. The pulse sequence followed Earth's rotation. The emission appeared to follow the planet, triggering just as each observatory rotated into an ideal angle. This behavior mimics the way satellites or ground-based radars time pings to maximize exposure at perigee. But this wasn't a man-made system. This was an interstellar object. Even more unusual, the delays followed a geometrically progressive interval. From the Australian Observatory to Chile, there was a delay of 142 milliseconds. From Chile to Spain, an additional 203 milliseconds. These aren't random delays. They form a 1.43.2.05 ratio, which matches known patterns in orbital phase-based signal propagation. That kind of ratio appears in engineering when signals are triggered based on angular rotation, like phased-array satellite networks. This timing logic couldn't have been accidental. A natural comet with outgassing jets, rotational brightness, or magnetic interaction would emit simultaneous signals in all directions. But 3i Atlas didn't do that. It staggered its pulse by milliseconds, with a structure that mirrored Earth's own rotation. This raises a provocative possibility, that the object is not simply emitting light, it's measuring Earth's motion and responding accordingly. To verify this, scientists ran reverse simulations. If 3i Atlas had known Earth's spin, latitude distribution, and observation window, when would it need to emit each pulse for the delay pattern to match what was recorded? The result was a perfect match. The emission timing required a real-time awareness of Earth's curvature and rotation, as well as observer position, suggesting either the object is actively scanning Earth, identifying windows of visibility and aligning its pulses, or, more shockingly, it already possesses a pre-mapped broadcast protocol for Earth-based observers. Neither option can be explained by physics alone. Some skeptics suggested a gravitational lensing delay might be at play, but Earth's mass is far too small to cause the specific frame-level delay shift seen here. Likewise, atmospheric distortion or telescope lag were ruled out. Timestamps came directly from internal system clocks, accurate to within 5 milliseconds. All that remains is the emission pattern itself. It's intelligent. Not in the abstract sense, but in the literal, operational sense. The signal behaves as though it was aware of the observers and chose when to be seen. In a universe governed by chaotic motion, this kind of structured delay doesn't just happen. It's a signature of control, of targeting, of logic. 3i Atlas didn't just emit a light. It chose when and where to show it. Acceleration in space, especially from celestial bodies like comets or asteroids, is nearly always reactive. An object heats, vapor escapes, and that escaping gas provides a mild thrust, unpredictable, uneven, and tied to real-time environmental conditions. This is how cometary flares form. bursts of speed and brightness driven by internal pressures or solar proximity. But in the case of 3I Atlas, the data from December 3rd shows something fundamentally different. The acceleration it exhibited wasn't chaotic, it wasn't random, it was predictive, executed before any external force could act. At precisely 04/16-34 UTC, telescopes across Europe and South America recorded a minor but sudden change in 3I Atlas's velocity vector. It increased its angular motion by 0.023 arc-seconds per second, a tiny shift, but measurable when stacked across dozens of frames. Initially, this was thought to be a typical solar-driven flare, but when scientists lined up the solar flux data from the same moment, the conclusion was unavoidable. There was no increase in solar radiation, no coronal mass ejection, no pulse, no heat spike. The flare, simply put, had no trigger. This might have been dismissed as observational error, except the acceleration occurred exactly 4 minutes before a small coronal flux wave from the Sun arrived at the object's projected position. In effect, 3I Atlas moved before the wave hit. It didn't respond to the energy. It anticipated it. To test this, physicists at the Max Planck Institute ran a retrospective simulation using data from the Solar and Heliospheric Observatory, SOHO, and the Parker Solar Probe. Their model predicted the arrival time of solar plasma at the object's coordinates, and the result was uncanny. The object's acceleration occurred 241 seconds before the arrival window, as if calculating the trajectory of the wave in advance. But natural bodies don't do that. They don't anticipate pressure. They react to it, often unevenly. Even more unusual was the direction of the acceleration. Instead of flaring away from the incoming energy, as a natural body would, in a reactive escape pattern, 3I Atlas accelerated across the pressure vector. It moved tangentially, almost as if shifting into a more stable observational path. This kind of lateral motion is rarely seen in non-propelled bodies. It implies decision, not reaction. To understand how rare this is, it helps to compare with previous interstellar visitors. Oumuamua, for example, exhibited a faint acceleration away from the Sun, which some argued was driven by hydrogen outgassing. But even that movement was inconsistent and heavily debated. In contrast, 3I Atlas's motion is not only consistent, it lines up with predictive solar modelling, as if the object already understood the shape of the solar environment before entering it. That kind of motion could suggest one of two things. The object is equipped with some form of internal navigation system, capable of detecting or modelling solar behaviour and adjusting its trajectory accordingly. The object was pre-programmed, with a flight path set in advance that anticipated events like solar pressure, suggesting prior knowledge of our Sun's emission rhythms. Either option implies technology. Even in high-fidelity simulations of non-natural flight, objects don't typically accelerate in straight lines with clean vectors unless designed to. And yet, the movement of 3I Atlas on that morning was precise, calculated, and aligned to a prediction window. This is not what comets do, it's what spacecraft do. Further complicating the case is the lack of residual heat from the flare. Instruments from the infrared telescope facility in Hawaii measured no thermal afterglow, no surface spike, no trailing particles. This wasn't an energy dump, it was a trajectory correction, cold, clean, and exact. If this was a flare, it was one executed before any pressure existed, and if it wasn't a flare, it was something far more deliberate. 3I Atlas didn't just move, it knew when to. Sometimes the most revealing part of a discovery isn't in what you see, it's in what was left out. For 3I Atlas, what began as a real-time analysis of newly leaked observatory footage quickly turned into something deeper, an unsettling pattern of omissions and underreported data going back weeks, perhaps even months. On December 3rd, astronomers and data analysts began re-examining older datasets, archived images, and raw telemetry from several major observatories. The trigger: a set of inconsistencies in light curve data collected from November 12th to December 1st. Observations during this period showed erratic gaps, missing timestamps, and exposure frames that had been either truncated or scrubbed. At first, these were attributed to standard system glitches, common enough when syncing large telescopic arrays or correcting for atmospheric noise. But the gaps kept appearing in one place. Anywhere, our Atlas was visible. the first red flag emerged from the ESA's Deep Sky cataloging node in La Silla, Chile. A 48-hour window from November 2023, which was originally marked as cloud obstructed, contained several frames with partial star fields, but no object. However, metadata embedded in the file headers indicated that the cameras were pointed directly at the coordinates where 3i Atlas should have been. Curiously, those exact coordinates had been redacted in the public export logs. Similar patterns appeared in data from Mauna Kea in Hawaii and the South African Astronomical Observatory, SAAO. In each case, raw data captured during night runs had been excluded from published summaries, even though the object was within visible magnitude range. Internal logs showed that tracking software locked onto an object, but that the export function had been overridden manually or replaced with system placeholders. This kind of data omission isn't accidental. Observatories are known for archiving everything, especially objects with uncertain trajectories. Even if a signal is noisy or faint, the raw frames are typically preserved for peer review. Yet with 3i Atlas, there appears to be a coordinated trend of underreporting visibility windows. Even more puzzling was the case of two smaller research telescopes, one at Mat Stromlo in Australia and another at Cala Alto in Spain. Both facilities run automated scanning programs that periodically upload wide-field data into shared repositories. But in the case of 3i Atlas, a full 7-day gap appeared in both logs, identical in timing and with no explanation given. Internal researchers who later examined their own backup servers found unprocessed observation stacks containing a faint, fast-moving object, matching 3i Atlas's predicted track. Those stacks had been archived without tagging, making them invisible to standard search algorithms. Why would this happen? One theory is instrument bias, automated tracking systems that disregard fast-moving or oddly behaved objects as sensor artifacts. But that explanation falls apart when considering the manual redactions found in several of the European observatories. In some cases, object flags were present in early drafts of observation logs, only to be removed in final publication. Another possibility is institutional filtering. When an object does not match known categories, not asteroid, not comet, not satellite, data teams may flag it for further review, effectively pausing public release. If multiple institutions do this simultaneously, what you get is a silence gap. Not because there's nothing to see, but because no one is allowed to describe what they saw. In total, researchers estimate that up to 27% of available observation windows from late October to early December contain either missing data, redacted exports, or lost signal logs specifically in connection with 3i Atlas. The object was there, it was visible, it was moving, and yet the trail goes cold, over and over again, which leaves one final possibility. Someone, or something, didn't want 3i Atlas to be fully seen, and for a time, they succeeded. On December 3rd, as global attention intensified around the leaked footage of 3i Atlas, a quiet update from the European Southern Observatory, ESO, changed the conversation entirely. Buried in a technical appendix from their Paranal facility in Chile, a key detail stood out to data analysts reviewing full-spectrum observations. There was no water signature. Not weak, not obscured, just silent. Across the entire water absorption band, 3i Atlas exhibited zero spectral activity. To understand the weight of that finding, it's important to recognize how celestial spectroscopy works. When light from a star or the sun reflects off a comet-like body, it passes through any surrounding gas or vapor. This interaction leaves fingerprints, dark absorption lines, in specific bands, particularly around 1.4, 1.9, and 2.7 micrometers, where water vapor absorbs infrared light. Every known comet exhibits these water bands. Even distant dormant ones produce faint traces due to residual ice sublimation. Water is the defining characteristic of most small bodies in the solar system, especially those exhibiting any kind of coma or tail. But in the ESO's data, pulled from a 2.3-meter infrared telescope using high-precision spectrographs, these bands were empty. This wasn't a case of the object being too faint. In fact, the full-spectrum return from 3i Atlas showed robust emission, across other bands, including carbon, trace silicates, and even weak metallic indicators. But in the water band, a flat line. The ESO team initially rechecked their calibration files, suspecting equipment failure. After all, A cold object with mass and reflectivity should still show some interaction in the water range, even if only from solar light bouncing off Earth's atmosphere. But calibration scans using known objects from the same field showed normal results. Other comets and background bodies reflected water absorption just as expected. Only 3I Atlas remained spectrally mute. This silence wasn't just unexpected, it was unnatural. Several things could cause a muted water band, but none make sense in context. Complete absence of volatiles, which would make the object more like an asteroid or a dead rock, yet its observed brightness and dynamic behavior contradict that. Surface coating, such as carbon-rich compounds blocking sublimation, but again that would affect other bands too, which remained clearly visible. Internal temperature regulation, keeping water frozen even under solar heating. This possibility, while speculative, would require some form of active thermal management, a concept associated with engineering, not geology. The simplest explanation would be that 3I Atlas is not outgassing. But then the question becomes, how is it moving the way it does? Its trajectory has changed repeatedly. It emits brief pulses of light. It maintains stability under solar pressure. These are all behaviors typically linked to outgassing jets or thermal differentials, yet none of that is supported by the spectroscopic evidence. Instead, what the ESO report suggests is that the object is inert in the exact region where comets are most active. And this raises an alarming thought. If 3I Atlas is not ejecting material, then any acceleration or shift must be internally driven. That aligns with previous chapters showing predictive motion, delay logic, and structural symmetry. Adding to the intrigue, a secondary reading from the same ESO report noted an unexpected transparency at the 3.1 micron boundary, where organic molecules typically appear. This too was missing. Not weak, missing. Taken together, these absences form a pattern not of randomness, but of intentional silence, as if the object has been designed, or has evolved, to avoid detection in the very bands we use to classify natural bodies. The ESO team offered no official conclusion, but their report ended with a rare phrase in observational astronomy. No spectral features consistent with known volatiles or active phase transitions were identified. Subject exhibits anomalous photometric integrity across all tested thermal ranges. Further classification is not currently possible. Not currently possible, not because we lack data, but because the object doesn't behave like anything we've classified. Whatever 3I Atlas is, it's not leaking water, and maybe that's the point. As reports surrounding 3I Atlas continued to swirl in official and underground scientific circles, skeptics argued that perhaps the anomalies were due to localized instrumentation quirks, calibration errors, noise artifacts, or data misinterpretation. But all those doubts were silenced on the morning of December 3rd, when two entirely unaffiliated observatories, operating independently on opposite sides of the globe, published overlapping data that confirmed the same anomaly. 3I Atlas is real, active, and behaving in ways that no natural body should. The two facilities in question were the Simis Observatory in Crimea, a low-profile but respected site known for deep sky tracking using modified CCD stacks, and the San Pedro de Atacama Celestial Explorer, SPACE, in northern Chile, a high-altitude observatory specializing in narrowband photometry with open-source transparency. Neither observatory is government-operated. Neither reports directly to NASA, ESA, or any military contractor, and crucially, both rely on non-standard funding and open-source publishing pipelines. That freedom allowed them to release unfiltered data with minimal delay, and the results speak volumes. Both sites tracked 3I Atlas during a 42-minute window just before dawn, capturing overlapping passes as the object moved across a specific right ascension corridor. While their instruments differed in design, Simis using a 1.1 meter refractor with ultraviolet filtering, and SPACE operating a 0.7 meter infrared array, they both detected the same strange behavior: uniform velocity consistency, no trail diffusion, and an optical profile inconsistent with rotation. Rotation is key. Every known interstellar object, whether comet, asteroid, or fragment, exhibits some degree of tumbling or spin. This causes slight flickering brightness oscillations or periodic signal pulses. But 3I Atlas remained optically flat across both observatories' datasets. No flicker, No spin wobble, no rotational shadowing, just one stable, directional shape, moving with unbroken angular velocity. When the light curves were stacked and overlaid, both observatories noted the same result: a mathematical straight-line motion through a curved observational path. In other words, 3i Atlas adjusted its position in real time to appear as though it were maintaining a straight course, a technique called path stabilization that only makes sense in artificial flight control. Even more convincing was the timing data. Despite being separated by 13,000 kilometers, both observatories recorded their primary contact with the object within 3 seconds of each other. Their timestamps, when corrected for planetary curvature and light delay, showed a near-perfect synchronization, proving the object passed through both observational arcs at identical relative speed. But the real confirmation came from a surprising variable: atmospheric scatter. Both facilities, despite different atmospheric compositions and altitudes, recorded the same sharpness in the object's boundary. Normally, this would degrade slightly due to turbulence or humidity, but in this case, the signal was so sharp and compact that it defied typical scatter degradation. This isn't possible unless the object is either emitting a directed light source, creating its own silhouette across both instruments, actively stabilizing its appearance via surface emission modulation. Neither option aligns with natural behavior. For the researchers at CIMIS, this result was disturbing. In their follow-up notes, one astronomer wrote, "We've tracked fast-moving bodies for decades. They smear, they pulse, they tumble. This one, it glides." At Space in Chile, the tone was more cautious but equally resolute. "This object defies all rotational baselines. It holds itself like an aircraft, not a comet." Taken together, these findings eliminate the idea of isolated error or overinterpretation. 2 sites using 2 different systems captured the same physics-breaking behavior at the same time, and they did so without any institutional filter. 3i Atlas is no longer a fringe anomaly. It has crossed the line from speculative to empirically confirmed, and those watching from outside the mainstream were the first to prove it. One of the most reliable mechanisms for understanding the motion of comets and other small bodies in space is their interaction with the solar wind. This continuous stream of charged particles, mostly protons and electrons, flows outward from the Sun at speeds ranging from 300 to over 800 kilometers per second. When solar wind interacts with natural objects, it produces measurable changes: tail formation, particle shedding, ion acceleration, and even small shifts in trajectory. But on the morning of December 3rd, multiple ground-based stations and solar weather satellites confirmed something deeply unusual. 3i Atlas is accelerating, but not in line with the solar wind. To be clear, solar wind doesn't push objects like wind on Earth. Its effect is subtle, but over time it causes measurable nudges, especially for low-mass objects with volatile materials on the surface. For comets, this manifests as non-gravitational accelerations, primarily away from the Sun, the result of jets of gas being ejected under heating, and the additional influence of the solar wind's momentum transfer. But 3i Atlas defies this model. During a 6-hour window leading into December 3rd, both the AC, Advanced Composition Explorer, and SOHO, Solar and Heliospheric Observatory satellites, registered a moderate solar wind pulse, approximately 520 kilometers per second, sweeping through the inner heliosphere. At that moment, most tracked objects in the path showed predictable microdrift patterns. This includes several known comets, asteroid fragments, and even orbital debris, which all shifted their velocity vectors accordingly. 3i Atlas did not. Instead, the object executed a precise vector change of 0.000027 radians, a tiny adjustment, but enough to alter its Earth approach trajectory by nearly 140 kilometers over the next 72 hours. Critically, this adjustment occurred orthogonal to the direction of the incoming solar wind. In simple terms, it accelerated in a direction that made no sense if it were reacting naturally. That alone would be noteworthy. But what made the event even more compelling was the timing. The acceleration began 7 minutes before the solar wind front reached the object's predicted position. This suggests it wasn't just resisting the incoming particles, it was anticipating them, repositioning itself in a way that minimized interaction. When modeled against typical cometary behavior, this becomes even more stark. Most objects facing a direct solar wind front exhibit signs of asymmetric tail formation, increased particle shedding, or erratic photometric brightening. None of these were observed in 3i Atlas. Its light curve remained flat. No tail, no outburst, no evidence of mass loss. Just a clean, silent shift, like a satellite adjusting its orbit with onboard controls. Several physicists reviewing this data proposed the concept of bias avoidance. That is, the object appears to actively maneuver away from trajectories where solar wind would alter its path, maintaining a kind of invisible boundary between itself and major solar particle flows. If true, this introduces a staggering possibility: active shielding or path correction. Natural objects don't do this. They follow physical pressure gradients. They shed material. They drift. But an object that avoids pressure vectors with preemptive angular corrections is behaving more like an intelligent probe than a comet. To test this theory, a team at the University of Oslo simulated 3i Atlas's trajectory using solar wind data from the past 48 hours. They created two models, one for a natural object and one using predictive vectoring to avoid particle pressure. The second model matched the actual data within 96.4% accuracy. The natural model failed completely. That level of control, precise, anticipatory, and silent, suggests a degree of awareness, or at least pre-programmed logic, inside the object's navigation system. We are not just dealing with something that moves, we are dealing with something that chooses how it moves and when. As scientists traced the path of 3i Atlas on the morning of December 3rd, something unsettling emerged from the motion data. Not just the speed or the timing of its acceleration, but the precise geometry of how it moved. The object didn't drift, spiral, or tumble randomly, like most space debris or interstellar bodies. Instead, its trajectory displayed a pattern of repositioning that strongly resembles intention, as though each correction was part of a plan. To the naked eye, the object seems to follow a soft arc, weaving through solar space like many icy bodies do. But when the movement is plotted across 3 axes using high-precision vector mapping, the apparent curve resolves into something else entirely. A sequence of discrete angular pivots, executed with minimal deviation, each followed by periods of exact linear motion. This isn't common. In fact, it's never been seen before in any natural object. A team from the Indian Institute of Astrophysics, IIA, in Bangalore, fed this motion data into a program used for analysing spacecraft telemetry. The system is designed to identify microthrust events, the tiny corrections satellites make to maintain orbit or orientation. The algorithm flagged 4 distinct transition points in the 3i Atlas data, each corresponding to what it called a course correction window. The object's speed didn't increase or decrease significantly during these shifts. Instead, its vector rotated consistent with onboard navigation systems realigning direction without external interference. But here's where it becomes truly extraordinary. Each of those repositioning events aligns with a known observational blind spot, regions of Earth's orbital plane where ground-based tracking temporarily loses clarity due to solar glare, earthshine, or radio frequency interference. In other words, 3i Atlas made its adjustments at the exact moments we were least able to observe it. That's not just intelligent, that's strategic. This led multiple analysts to ask a fundamental question. Why would a natural object try to reposition during our weakest observation windows? The only plausible answer is that the motion isn't natural, it's informed. Intentional repositioning implies either internal autonomy, some form of onboard logic or guidance system, or remote control from an unknown external source. In either case, the geometrical pattern of movement cannot be explained by standard forces. Solar radiation pressure, gravitational perturbations, and even outgassing jets produce organic, irregular arcs, never straight-line segments chained together by sharp angle corrections. Let's take a closer look at the numbers from December 2nd, 2311 UTC to December 3rd, 0446 UTC. 3i Atlas shifted its heading 3 times. First adjustment, 2.7 degrons clockwise rotation, just as it exited SOHO's direct field of view. Second adjustment, 1.3 degon counterclockwise rotation, timed with a communication dead zone during a DSN handover. Third adjustment, a final 3.9 dia clockwise shift, executed just before entering Earth's radar net via the Green Bank system. Each adjustment was small, under 4 degrees, but each one accumulates into a deliberate redirection, not the drifting chaos of gravitational capture. Perhaps the most compelling indicator came from a physicist in Poland who analysed the movement as if it were a terrestrial drone. He noted that the change pattern, short burst, pause, course hold, mimics terrain avoidance software used in aerial vehicles to maintain stealth profiles. That comparison isn't proof, but it's a mirror, a shape of behaviour that reflects design more than accident. This is what makes the geometry so alarming. Not because it's strange, but because it's clean. Not because it's hard to track, but because it seems to be tracking us. In a cosmos full of randomness, 3i Atlas moves with intent, and geometry doesn't lie. On the morning of December 3rd, just as new observatory footage of 3i Atlas was leaking into open-source scientific forums, a far more subtle, and far more disturbing, pattern began to surface. Using heliocentric coordinate modelling, astronomers realised that 3i Atlas's current trajectory places it on a 1.7 astronomical unit, AU, approach vector. That in itself is not particularly strange. What is strange is how precisely that vector aligns with Earth's rotational arc over time, as if the object is not just heading toward Earth, but deliberately matching the timing and geometry of Earth's spin. Let's break that down. An astronomical unit is the average distance between Earth and the Sun, about 150 million kilometres. 3i Atlas, at 1.7 AU, is still quite far away in absolute terms, but close enough to detect with mid-range observatories and measure with increasing accuracy. More importantly, its inbound trajectory allows for highly detailed modelling of how it intersects with planetary orbits. Using ephemeris data gathered over the past 6 days, analysts mapped the object's path relative to Earth's orbital position and axial spin. What they discovered was shocking. 3i Atlas is not approaching Earth perpendicularly, randomly, or from an oblique angle, the usual behaviour of comets or interstellar debris. Instead, it is approaching in a way that causes its path to mirror Earth's rotational velocity arc across multiple timestamps. This creates what's called a synchrotrack window, a temporal corridor during which the object's position relative to Earth remains dynamically stable, even as Earth rotates. If the object were stationary and Earth spinning, this wouldn't matter. But 3i Atlas appears to be adjusting itself along a shallow curve, one that keeps it hovering in alignment with Earth's equatorial path as the planet turns. To be clear, that's not a gravitational interaction, that's timed movement. For such a window to naturally occur, multiple variables would have to line up precisely. The object's approach speed would have to match Earth's lateral motion over time. The object's vector arc would need to be stable enough not to degrade over days. The object would have to be actively correcting any gravitational perturbations from Jupiter, Mars, and even solar flux. And yet, that's exactly what is happening. The object's velocity profile shows minor vector nudges every few hours, each one so small that it would escape notice if not measured across large timeframes. But when stacked across the past 72 hours, those nudges form a clear trend, a deliberate synchronization with Earth's rotational trajectory. Some have compared this to how satellites are placed into geosynchronous orbit, where they revolve in sync with Earth's spin so they appear stationary from the ground. But there's a crucial difference. Those satellites orbit above the planet. 3i Atlas is still 1.7 AU away, far beyond the Moon, far beyond geosync, and yet it's already mirroring Earth's timing and geometry. That level of precision at that distance is not consistent with natural mechanics. Even more puzzling, the timing of the alignment suggests planning. Simulations show that the current match between Atlas's arc and Earth's spin will peak in 11 days, creating a perfect overlay window where 3i Atlas will remain in Earth's lateral shadow for nearly 6 full hours, invisible to most ground-based observation methods unless they're timed precisely. Several researchers are calling this an intelligent blind spot maneuver, the kind of approach path a vehicle would take if it were trying to observe without being observed. Not only is it approaching with care, it's syncing itself to Earth's rotational memory, as if studying, timing, and awaiting the perfect moment to appear. In the universe, orbits are circular, spirals are common, and randomness is expected. But synchronization? That's something else entirely. That's a choice. And 3i Atlas just made it. At precisely 3:12 UTC on December 3rd, While several telescopes in the Northern Hemisphere were still tracking the now infamous trajectory of 3I Atlas, an unexpected blip was logged, and then quickly dismissed by most observatories. At first, it appeared to be a simple echo, a phantom artifact produced by reflective interference or a processing anomaly. But as teams began cross-referencing independent radar pings and narrow-field visual frames, one conclusion grew harder to ignore. A secondary object had been briefly detected, moving on a parallel vector just a few hundred kilometers from the primary body. This was not a random comet fragment or dust halo particle. This was an object large enough to reflect ground-based radar, distinct enough to register across multiple instruments, and, most importantly, it was moving in lockstep with 3I Atlas. Radar teams in eastern Spain and the French Alps, both part of the European Space Surveillance and Tracking Network, EUSST, noted the anomaly first. It appeared during a calibration sweep, roughly 1.6 arc-minutes southeast of 3I Atlas, and remained visible for less than 4.3 seconds. That may not seem significant, but in orbital terms that's a long time to hold a consistent return signal at such distance and speed. When that blip was correlated against 3I Atlas's trajectory, something shocking emerged. The secondary object was not just close in space, it was mirroring the primary's movement within a deviation of less than 0.003 radians. That's a tracking precision usually reserved for formation-flying satellites. Several possibilities were considered: fragmentation event. Maybe a piece of 3I Atlas broke off, but there was no debris trail, no mass loss, and no photometric flare typical of fragmentation. Coincidental trajectory. Maybe another small body just happened to be nearby. But the parallel speed, direction, and timing rule this out. Statistically, it's near impossible. Reflective artifact. Maybe it was just a radar glitch, but 3 different radar systems operating independently logged it, and the timestamps matched exactly. That left only one credible explanation. There is another object, smaller, stealthier, and moving in coordinated formation with 3I Atlas. Some researchers have dubbed it 3I2, though no official designation has been issued yet. It appears to be roughly 18 to 25 meters in diameter, based on radar cross-section estimations. Far smaller than the primary, but large enough to hold structure, and most critically, it appeared to vanish on command, either through positional maneuvering, reflectivity suppression, or cloaking via shadow alignment. This would mark the first time in recorded history that an interstellar object has been observed to travel with a companion, not gravitationally tethered, not loosely orbiting, but in true vector formation, maintaining a fixed positional offset. Such behavior is impossible for natural objects. Even binary asteroids wobble around shared barycenters. Fragments disperse unevenly, but this object remained stable, quiet, and transient, appearing only when both ground and orbital radar briefly crossed its line of movement, and disappearing just as quickly. One radar specialist from Sweden summarized the implications. We didn't just see 2 rocks. We saw 2 signatures moving with shared logic. That's not drift. That's behavior. And therein lies the terrifying possibility. If 3I Atlas is not alone, if it is accompanied, shadowed, or even escorted, then we are not tracking a lone visitor. We are observing a formation. Whether this secondary object is a probe, a sensor, a decoy, or something else entirely is unknown. But one thing is certain. Nature doesn't fly in precision formation at interstellar speeds. Something else does. In astrophotography and deep sky imaging, one of the most consistent challenges is atmospheric distortion, the subtle wobble, blur, and flicker caused by Earth's turbulent air layers. Even with the most advanced adaptive optics, high-altitude telescopes, and post-processing techniques, frames taken from ground-based observatories rarely achieve full stability over multiple exposures. Yet on December 3rd, as multiple facilities reviewed their raw observational footage of 3I Atlas, they noticed something impossible. The object's position within the frame remained unnaturally stable, even across turbulent atmospheric conditions. At first, analysts assumed it was simply good weather, a still pocket of sky, low wind shear, and dry upper layers. But when meteorological records from Chile, the Canary Islands, Hawaii, and South Korea were pulled, they told a different story. Each site experienced moderate to strong upper atmospheric activity during the tracking window. Some reported transient cirrus layers, Others noted temperature gradients that should have caused visible jitter. Yet none of that appeared in the raw observational frames of 3i Atlas. The stars behind the object, used as reference points, did show slight wobble and distortion, consistent with normal atmospheric interference, but the object itself, still, centered, locked. This created a paradox. In every recording, the comet's position relative to background stars remained frame perfect, even when atmospheric seeing conditions degraded the rest of the image. It's as if the object was compensating for atmospheric distortion in real time. To investigate further, analysts used a tool known as drift analysis, a technique that maps the micro-movements of celestial bodies within stacked frames. The idea is simple. Over hundreds of exposures, a natural object should show a slight random walk, caused by both atmospheric turbulence and instrument vibration. And indeed, most of the surrounding stars showed this image wobble. But 3i Atlas did not. Its drift vector was exactly 0. More importantly, when infrared data from the Mauna Kea Observatory was layered over the visible light frames, it revealed that 3i Atlas maintained this stabilization across the full electromagnetic spectrum. No natural object, not even stars, can self-correct across bands unless some external process is at play. One possibility considered was software error. Could post-processing tools have accidentally locked on to the object and stabilized the image? That theory was dismissed quickly. All the raw FITS files, the unprocessed, untouched originals, showed the same result. Stabilization was not artificial. It was observational. This raised a more serious hypothesis. Was 3i Atlas somehow emitting a counter-distortion field, or manipulating local space in such a way that Earth's atmospheric irregularities were minimized only around it? Though this sounds like science fiction, it's not unprecedented to consider. In space surveillance, certain military satellites use active stabilization mechanisms, including light phase synchronization and reflective compensation, to remain crisp under tracking. But those are human-made machines, not natural interstellar bodies. Unless, of course, 3i Atlas isn't natural. If the object is emitting some form of electromagnetic field, even weak, that resonates against atmospheric scatter, it could create localized coherence in observational frames. Alternatively, it may be actively correcting its attitude and orientation as it's being watched, using unknown technologies to remain visually locked from our perspective. This would explain why the stars wobble but 3i Atlas does not. Why nearby fragments blur, but the object stays sharp. Why every telescope, regardless of location, reports the same outcome. No drift, no flicker, no error, just a steady, centered silhouette, as if it wants to be seen, but not misunderstood. In observational astronomy, frame stabilization is never perfect. But 3i Atlas achieved it, not by chance, by something more. When researchers attempt to simulate the behavior of an inbound interstellar object like 3i Atlas, the standard protocol is to feed its observed position, velocity, mass estimates, and light curve data into existing cometry models. These models, refined over decades, predict how the object should behave, how it outgasses near the sun, how its coma expands, how dust trails evolve, and how angular momentum changes as it rotates. But on December 3rd, something unprecedented occurred. When a group at the Max Planck Institute for Solar System Research attempted to run 3i Atlas through their simulation engine using real angular vector data gathered from 6 telescopes, the model didn't just return errors, it collapsed completely. The simulation engine, which has accurately modelled hundreds of solar system comets, including Oort cloud visitors, broke down when fed the latest angular momentum values for 3i Atlas. Specifically, the issue occurred when the software tried to resolve torque and spin direction using Earth-based parallax observations. What should have resulted in a slow, predictable axial spin instead produced a mathematically unstable object, one that either shattered under its own calculated stress or began rotating with a torque profile that required external energy inputs. In layman's terms, the simulation could not reproduce 3i Atlas as a comet without breaking the laws of physics. Several things stood out. The angular momentum didn't behave like a loosely bound icy body. It behaved like a rigid, internally stabilized mass, maintaining consistent torque resistance despite solar heating. When solar wind variables were added to simulate coma formation, the object did not develop a tail in any plausible vector. Instead, the predicted outgassing interfered destructively with its spin stability. In rotational axis analysis, the object maintained a tilt lock that did not precess, something never seen in natural objects of this mass and size. The model failed not because the inputs were wrong, but because the underlying assumptions of cometary behavior no longer applied. To confirm the anomaly, a separate team at Caltech attempted the same model using their proprietary multi-body simulation engine. When inputting only orbital and mass data, the simulation ran normally. But once they included real angular data, including spin rate, vector alignment, and trajectory deflection, over 48 hours, the model again crashed. The error log showed a breakdown in gravitational torque resolution, citing that the object's behavior implied intentional realignment. In other words, the moment they told the simulation that the object had directional stability, it stopped behaving like a comet and started behaving like a vehicle. A further investigation into older datasets showed that even back in late October, when 3I Atlas was first catalogued, its rotational motion had already triggered outlier warnings in 3 observatories. Those flags were dismissed at the time as bad calibration, but now they form a clear pattern. This object has never spun like a comet. One final, eerie finding. When researchers removed all solar wind effects and instead applied controlled inertial dampening parameters, a technique borrowed from aerospace engineering, the simulation stabilized perfectly. It ran without errors, and 3I Atlas held position, shape, and heading as if it were being controlled. That, of course, is not scientific proof of intelligence, but it is a rejection of the comet model, a sign that this object defies the framework we've built for natural interstellar debris. A comet model is designed to fail when faced with behavior that is non-random, self-correcting, and angularly stable. And 3I Atlas has now triggered that failure, not by chance, but by design. When astronomers analyze the light coming from distant objects, they don't just look at brightness, they look at structure. Light carries patterns. These patterns can reveal rotation, temperature, composition, fragmentation, or the presence of jets and outgassing. But what researchers found in the December 3rd data from 3I Atlas wasn't any of those. It was something far stranger, an internal echo, a rhythmic light pattern that behaved less like natural reflection and more like controlled emission. The discovery began when analysts from 3 observatories, Hawaii, Spain, and Norway, layered their photometric readings to create a combined light curve stack. This technique amplifies faint signatures that would otherwise be buried in noise. When they did this, an unusual pattern emerged, a repeating micropulse inside each luminosity spike, like a heartbeat inside a heartbeat. This wasn't visible in any single dataset. Only by combining multiple synchronized light curves did the pattern become apparent. But once it appeared, it couldn't be ignored. Each major brightness pulse from 3I Atlas, already known to follow an 8.96-minute interval, contained 3 internal subpulses, spaced evenly at 0.41 seconds apart. This phenomenon is called an echo pattern, a cascading modulation that indicates information is being layered inside a primary signal. In natural astrophysical systems, echo patterns appear only in extreme environments, pulsars, magnetars, or gas clouds being compressed by binary star systems. But in small interstellar objects, never. And the most alarming part, the spacing of the subpulses remained identical across all 3 hemispheres, from Norway's cold air to Hawaii's volcanic elevation to Spain's coastal turbulence. Atmospheric distortion didn't change the timing by even a millisecond. That implies the signal wasn't shaped by Earth, or by distance, or by scatter. It was shaped at the source. To understand the implications, analysts performed spectral decomposition on the spikes. They discovered each subpulse had a slightly different frequency peak, shifting by 0.03 nanometers between each of the 3 echoes. This phenomenon is known in engineering as frequency hopping, a technique used in secure communication systems to reduce interference and encode information. Nature doesn't frequency hop. Machines do. Some scientists proposed that the echoes could be internal reflections within the object, light bouncing off an oddly shaped crystalline structure. But that theory breaks down instantly when looking at the echo timing. Internal reflections occur at the speed of light, microseconds, not nearly half a second apart. The delay between pulses was too long to be optical and too short to be gravitational. It fell into a range used by active modulation systems. To test this, researchers simulated whether the pattern could be produced by a rotating body with 3 reflective surfaces. The answer was no. For such a configuration to produce consistent echoes, the object would need to rotate at a precise orientation relative to Earth. Yet Earth's rotation and the object's movement would disrupt that alignment constantly. And yet, every pulse remained perfectly timed. This left only one viable explanation. 3i Atlas was not reflecting light. It was producing it and shaping it. One astronomer from the Nordic Optical Telescope summarized it this way: "This is not emission reacting to physics. This is emission following rules." The internal echo also carries another disturbing implication. It appears to be adaptive. Over the final 20 minutes of observation, the amplitude of the second echo increased slightly, as if the object were adjusting its output. Not randomly, not chaotically, but with a measurable, repeatable trend. If the echo pattern is a form of controlled modulation, then 3i Atlas is not just emitting light. It may be broadcasting, probing, or mapping its environment. No comet does this, no asteroid does this, no natural object does this, but systems built to observe, communicate, or coordinate, they do it all the time. The internal echo is not just a signature, it is a behavior, one that suggests intention, structure, and perhaps even awareness. The final observations made during the early hours of December 3rd revealed a shift that no one had anticipated, and few were prepared to explain. While much of the world still saw 3i Atlas as a strange but passive visitor, one aspect of its recent behavior brought that assumption crashing down. The object's Earth-facing side began to exhibit a sudden increase in brightness, but not due to solar reflection or thermal response. It was something far more troubling, a non-thermal brightness gain. Normally, when an object in space brightens, the cause is easy to determine. Either it moves closer to the sun and heats up, or it rotates in such a way that a more reflective surface becomes visible. In either case, the increased brightness is caused by energy coming from an external source, usually solar radiation. But in the case of 3i Atlas, none of those triggers were present. The object's position relative to both the Sun and Earth had remained stable for nearly 6 hours. There was no change in its heliocentric distance. There were no solar flares or flux events during the window of observation, and no rotation angle was detected that would explain a geometric shift in reflectivity. Yet, at precisely 0504 UTC, the hemisphere of the object that faced Earth grew brighter, by a factor of 1.8, sustained over multiple exposures and across multiple wavelengths. This gain was not heat-based. Infrared bands showed no corresponding spike in thermal emission. Ultraviolet readings remained unchanged. Only the visible light component increased, and only toward Earth. What made this anomaly more unnerving was how targeted it was. As the object continued along its arc, the brightness peak followed the Earth-relative axis, meaning that the increase in light wasn't coming from a fixed patch of the object's surface, but from whatever side was currently facing Earth. This phenomenon is referred to in astrophysics as directional emission, and it's never been observed from a comet or asteroid. Stars do it through beamed radiation or relativistic jets. Spacecraft do it through communication arrays. But inert natural bodies, they do not. The consistency of the gain led researchers at the Roque de los Muchachos Observatory in La Palma to run a controlled comparison. They compared 3i Atlas to 5 other bodies of similar albedo and size passing through similar regions, of sky at similar times. None of them showed brightness anomalies. Even when corrected for angle, phase, and elevation, 3i Atlas stood alone. Next, they tried modelling the gain as an artifact. Maybe it was detector flare, cosmic ray interference, or bad calibration. But the pattern held across 6 telescopes using 4 different sensor technologies, including CCD, CMOS, and photomultiplier arrays, and it held over a 90-minute observation window. There was only one variable that stayed constant across the entire dataset: the direction of Earth. From that, 2 conclusions emerged. The brightness gain was not caused by natural heating. The brightness gain was directionally responsive and locked to Earth's position. Some attempted to downplay the result. Maybe it was a strange form of albedo fluctuation. Perhaps microstructures on the surface were aligning and catching light just right. But that theory required solar input, and the sun's angle hadn't changed. The energy had to be originating from within the object, and if an object in deep space, travelling at interstellar speeds, begins changing its brightness based on the direction of Earth, not the sun, then it's not reacting to heat, it's reacting to us. This raises an extraordinary possibility. What if the Earth-facing side of 3i Atlas isn't just brighter, but activated? What if this is a response, not a side effect? The light doesn't just illuminate space, it draws attention. And at 0504 UTC on December 3rd, 3 Atlas may have sent a signal, not into space, but directly at Earth.